Welcome back. And the topic this week is to try to wrap up this discussion on perturbation theory. And we are going to list the basic diagram rules. And then we are going to look at some examples. And we are going to, in terms of time-independent perturbation theory, we will state the so-called link diagram theorem. But then we are going to discuss that in more detail when we come into time-dependent perturbation theory. Now, in the textbook of Shavit and Bartlett in chapter 6, there is a proof of the link diagram theorem. We will discuss examples of that today for time-independent perturbation theory. This proof is often very convoluted, and sometimes it's easier to see that when you have introduced time-dependent many-body theories. And we will use that to actually catch two birds with a stone. One is to develop the time-dependent formalism, which is needed for Green's function theory. So when we now move over to Green's function theory, which is the last topic we will cover this semester, we need time-dependent expansions and representations of many-body theories. So some of you may have met these topics already. You probably heard about these so-called pictures. It's called a Schrödinger picture. You have a Heisenberg picture, and then you have the interacting picture. And we are going to just set up that way of rewriting Schrödinger's equation, because that's useful when we come to Green's function theory. And then with a time-independent approach, we can also develop time-dependent perturbation theory. And that is often a little bit easier to use in order to understand the so-called link diagram theorem. Because when you look at that from a time-independent approach, then it's often a little bit more difficult to realize what the theorem is about. So what I want to do first today is to run through the diagram rules, how we can calculate higher many-body contributions, many-body perturbation theory contributions, and then we're going to look at some explicit examples. And in particular, an example which allows us to make a link between Bruyne-Wigner perturbation theory and the exact solution, and Rayleigh-Schrödinger perturbation theory, so that you see the differences between the two ways of performing the Taylor expansion. One Taylor expansion is in terms of the exact energy, and the other one is in terms of the unperturbed energies, which is Rayleigh-Schrödinger perturbation theory. Now, the second midterm is also something which we will spend time on tomorrow. And this second midterm is a mix of FCI, what we did in the beginning of the semester, Hartree-Fock theory, and many-body perturbation theory. And it's a model which has been widely used in condensed matter physics, but also in nuclear physics. And it's called the pairing model. And it's a model which allows us to understand in a more intuitive way different types of correlations. And the case we are going to look at is a case which can be diagonalized exactly. Also, there is a part on Hartree-Fock theory, but you will realize rather quickly that you are already in a Hartree-Fock basis. So one of the exercises is actually an exercise where you don't need to do many calculations. But you will see that when we start discussing the topic. And so you can fetch, if you open your email, you will probably see that you got an email with a second midterm. So I put a tentative deadline till next Sunday. But if you guys are having problems with crashes with other courses, we are always flexible with an extension. So I put it to next Sunday in order to avoid you having crashes with other exams. But in case we need more time, there is no problem with that. But we should try to finish by December the 1st. Because else, you guys are going to be pretty stressed with exams. And the other thing is that the oral examination, as we agreed on last time, seemed to fit with December the 19th. And this is something we can do via Zoom as well. So if you are back home, you can always connect and then via Zoom. So if you're not here, there is no problem in running the exam. So just let me know if other days are better, because both Stian and I, who will be the examiners, we have maximum flexibility in those days. The other thing is that the final oral examination would be you making a presentation of 25-30 minutes. And it's pretty natural to make a presentation where you could use the two midterms. And then you would discuss the different money-body theories we have gone through, and then make a presentation of, let's say, midterm 1 and midterm 2, where you discuss FCI theory, Hartree-Fock theory, money-body perturbation theory. And if you wish to bring in Green's function theory, for Green's function theory, we are not having any exercises, or it's not the topic of the midterm, but you can always discuss the theory if you want to. Yeah.
Yeah. Are there any things that had to be inside this presentation? Do you have any like list of things?
So you should present the money-body methods we have discussed, and you can discuss the pros and cons. So like last year, people started with second quantization, and then they went through FCI theory, Hartree-Fock theory, money-body perturbation theory, and last year we had copper cluster theory. And then they explained the differences, the pros and the cons. And then you could use some of the results from the midterms to actually illustrate the theories and what they mean. So that means that I don't like this setting where we, test you with different types of questions, because people can often, shit happens. And it's much easier if you give a presentation, then we have questions about the presentation you make.
We should make like a brief summary of the course.
Yeah, so in a way, it would be a summary where you talk for, let's say, 25 minutes, 30 minutes, roughly. And then we have 15, 20 minutes of questions. And that's 45 minutes in total. Yeah. So just let me know if that format is okay. Hopefully it's more relaxing, because then we would have a discussion based on the insights you've gotten and the way you present them. Okay, so I'm going to switch over to the whiteboard, because these are notes which I haven't put into a nice LaTeX format, except for the slides which we have for tomorrow. But let me say something now about the diagram rules. So last week we looked at examples. Now we are going to summarize this into a set of rules which can be used to analyze terms in money-body perturbation theory. So if we now just write down these different rules, there are a set of rules which will then allow us to extract immediately an analytical expression for a given contribution to money-body perturbation theory. And these kind of diagram rules are used also in Green's function theory. It's pretty common when you do Green's function theory to look at diagrams. And the same is if you're doing copper cluster theory, if you're doing other methods like renormalization group methods, etc., etc. It's very common to express the different contributions in terms of diagrams. And then you can always interpret a diagram as some kind of money-body contribution to a given state. So the first rule, so let's just write down. So I'm gonna write down in a pedantic way here the different contributions. So for a diagram, and since we are expanding in terms of the interaction itself, so with a given number of vertices, so it can have n vertices or NH1 interactions, HI interactions. Then what you would draw then first is actually draw these n so-called vertices. And this is something which I'm going to try to catch two birds with a stone. So I'm going to introduce time here, because you can think of when you draw these different vertices as interactions happening at different times. We have not introduced time here, But when we do time-dependent perturbation theory, this comes out naturally. And this is a natural interpretation of the different physical processes. So in many-body perturbation theory, the most common way to present it is normally with time-independent theories. But when you move to Green's function theories, then it's natural to bring in time. So when I say time now, it's a kind of time in quotation marks. But when we start with Green's function theories, then time is the way we are going to use in order to see how the system evolves. So we would then plot at different times vertices at times. And then we would have a time t0, which is larger. So this would be the final time, larger than t2, larger than previous times, and then finally larger than some time t of n, which would be our time far away back. So each vertex can be a anti-symmetrized diagram or an anti-symmetrized interaction. So when we talk about these vertices here, each vertex can be either an anti-symmetrized matrix, an anti-symmetrized, or symmetrized, or not interaction. So if you use anti-symmetric interactions, then we would typically use Hugenholz diagrams, but it's pretty common to open them up because Hugenholz diagrams can be very compact in the way we draw them. And you would typically indicate that or not, indicated by, if we do a Hugenholz diagram, it would typically be a blob like this, or just an interaction with dotted lines like this. And this is in the case of a two-body interaction. So we can have two-body interactions, or we can have three-body interactions, but we're assuming that we have a two-body interaction only. Or a one-body interaction, or vertex, as it's often called, which we would typically label with something like this. Or you may see something which looks like this. So this depends on what you actually mean by that. So there are different notations here. Then we are going to have a rule 2 here, which is drawing all topologically distinct diagrams. And I will give you an example of what we mean by that. We saw examples last Thursday. So let's just put this up. This is rule 2 here. So draw all topologically distinct diagrams. Topologically distinct diagrams. By linking up particle and whole lines with different vertices, with various. And when I say vertices now, this can be two body, one body, or three body, or higher body one. And when we say topologically distinct diagram, so we would say that two diagrams are topologically equivalent, can be made topologically equivalent by deformation. And I will show you an example of what we mean by that. Deformation of fermion lines. Under a specific restriction, under the restriction So let me just write that one down. That restriction, that the time ordering we've chosen, that the ordering of the interactions is kept, of the interaction vertices is kept, or the ordering of the diagram is kept. So if we have ordered the interactions in these vertices in a specific way, we want to keep that because it means that there is a kind of time ordering which takes place. So the interaction, the system interacts at a time t1, and then it interacts again at a time t2, and then at a final time t3. So that ordering is being kept, the way the interactions follow. So the ordering of diagrams is kept, and the other thing is that particle lines should stay particle lines, so we cannot change a state above the firm level to a one below. Particle lines stay particle lines, stay as they are. This applies the same to whole lines. And then the ordering at the final time and at the initial time, when we're looking at this physical process in terms of a diagram or a set of repeated interactions, that is not changed. So you start the system in an unperturbed state, there is an interaction, and now I'm anticipating this discussion about the adiabatic hypothesis, the way we switch on the interaction adiabatically. That is a basic assumption in perturbation theory, and also Green's function theory and many of these many-body methods. And we will discuss that a little bit more tomorrow. But the idea then is that you start with your system at a time infinitely back, and then the system interacts, and then this keeps interacting, and then it gets back to a given state at a final time. So that kind of ordering with final time and initial time is not changed. So, so whole lines stay as wholes. Whole lines are kept. And then the order of the vertices at the time at t0 and at this time way a long time ago, which you could think of time infinitely back. So t0 could be you making a measurement at time t equals 0, and then you have a time infinitely back when the system was not interacting, and then you let it interact. So these are some of the basic assumptions which are used when you're setting up this type of diagrams, and Tn are not changed. So let me give you an example here of what we would call an equivalent diagram. So let's take a look at that. So suppose we now look at the diagram we had last week, the two-particle, two-hole excitations in many-body theory, many-body perturbation theory. So we had a diagram which looks like this. Now, if we use anti-symmetrized matrix elements, this diagram is equivalent, the expression. So if we take this diagram here, if we use anti-symmetrized matrix elements, what we found last week when we calculated the different contractions is that this diagram, if we now put labels, so this would be I and J, and then we have A and B, and then I have my I and J here. They are just unchanged. But then I get now a exchange term, which comes from exchanging. So we have, in this type of diagrams which we have here, what we have is a one piece which is calculated by the direct matrix elements, and the other one which is calculated by the exchange part of the matrix elements, where we now exchange two particle states. So this is A and B. So when we now using anti-symmetrized matrix elements, anti-symmetric matrix elements, which is pretty common, elements we can shrink this, we can rewrite this. Right, both. They have the same expressions, so we would then shrink the vertices to just these dots. So we are using the Hugenholz representation. So we have two particle lines, A and B, and then we have the two whole lines here. This is I, and this is J. So we say now that this diagram A and this diagram B, if we are using anti-symmetrized matrix elements, they are equivalent. If we are not, then they're not equivalent. Then we have to be careful. So it's common to actually use what we call anti-symmetrized matrix elements. Because then when we shrink these into just this Hugenholz representation, then the theoretical expressions are exactly the same. So we can now, if you look at the rule here, by linking up particles and whole lines with various vertices. And they can make topological equivalent by simply the formation of fermion lines under the restriction that the ordering of the diagram is kept. So the ordering here is kept. In this specific case, we are deforming A and B, which reflects the fact that we have an anti-symmetrized matrix elements. So here we are looking at the direct element multiplied with the exchange element. Now, when we now use anti-symmetrized matrix elements, these two give the same expression. So that means that I can go from this compact notation and I can open up this diagram like this, or I can open up like that. So it's pretty common to use these diagrams instead of that one, because this becomes very compact and sometimes the readability is less than if you open up the diagram like this. So in many textbooks, you will actually see this one being drawn as this one, assuming that the matrix elements are antisymmetric or antisymmetrized matrix elements. So just keep that in mind, that in many textbooks, they often, when they calculate this diagram here, they're often thinking of this one. And this is just a little bit unfortunate notation. Alternatively, you would have to, if you're not using anti-symmetrized matrix elements, you would have to draw this one and that one. Now, this one has an exchange which is equivalent in expression. And this one also has a case where we can exchange A and B and I and J, and that would be totally equivalent if we use not anti-symmetrized matrix elements. So if this is the starting point, then these two and two other matrix elements, two other diagrams are equivalent. So the other two equivalent ones to this one would then be this diagram here, which we drew last time, which looks like this. So we have the I and A, and then we have this other one, where we now have J and B. And then we have another one, which looks like this. So the interactions are unchanged. Particle lines stay as particle lines. But now we could have the two particle states where we keep the direct term, but then we can have the exchange for the whole lines. So this will be I and J here. So this diagram, which you see here, if we are not using anti-symmetrized matrix elements, then this diagram here is equivalent with this diagram here. Where we have A and B and I and J. And you can see that if we now use the diagram rules, because when we set up the matrix elements, if we only look at the matrix elements, so let's call this for A and this one for B, when we only look at the matrix elements, in A, we are going to have a sum of A, B, I, J, and then we are going to have the matrix elements in Ji, of B, A, of BA, or V and JI. And these are now, if these are anti-symmetrized, then the two are equal. But if they are not, so I'm not putting an AS here now. If I look at B without looking at the energy denominators in the other terms, that is given by AB of V of IJ. So the order here doesn't matter actually. But what happens now is that this matrix element you see here, due to the permutation symmetries, this is the same as IJ of V of AB, which is this matrix element. And then we have the other one, which is also AB of V of IJ. So if I'm not using anti-symmetrized matrix elements, then these two would be topological equivalent. And it doesn't matter which one I count. And if I look at this diagram, this will be equivalent with this one. And you can see that when you look at the matrix elements, due to the permutational symmetries which you have in the two-body matrix elements. So that's just a kind of discussions which can make life a little bit difficult in the beginning when you're thinking of topologically distinct diagrams, because you have to define whether you're using anti-symmetrized matrix elements or not. And this equivalence comes from the fact that you have a symmetry in your interaction matrix elements. If you didn't have that symmetry, this would not apply. Okay? So when we say topologically distinct diagrams, that is something which has to do with the fact that the matrix elements you're using have specific symmetries. And if we deal with anti-symmetrized matrix elements, then this one, and this one, they give exactly the same contribution. And then you would simply draw it like this. Okay, so that was a little bit about topological equivalence. We have other diagrams, another example, if you want to look at that one. So we can have an example like this, which we saw last time. So we have a whole line. This is the one particle, one hole excitation, which we have. So we would have a state I, a state J, and then we have a state A and a state K here. So if you're using anti-symmetrized matrix elements, this diagram here is topologically equivalent with this diagram which we have here. So I could now have a particle line which goes up here, but then I have a whole line where I now link this one like that, so K here, and then I have the whole line here of this J. So this should actually go like this. So that's a diagram. When I now use anti-symmetrized matrix elements, this is are just examples of how I would open up this matrix element which you see here, which is a more compact way of writing the above expressions. Okay. Yeah. So this is just another example of topological equivalent diagrams. And when you look at the one, so this is something which we normally call a one particle, one hole contribution, because we have an intermediate between the two interactions. You could think of now the system being in the ground state, and you create a one particle, one hole excitation. So the interaction produces an intermediate state, which is a one particle, one hole Slater determinant. And then after some time, this gets de-excited and you go back to the ground state. And then you delete the one particle, one hole state, and you're back in your ground state. So this is a very compact way. This diagram, which you see here, is a very compact way of illustrating a process like this, where you start with the ground state. So this is a contribution to the ground state expectation value to a second order perturbation theory. And then you have an interaction here, which is a one body type of Hamiltonian. And this can create an intermediate one particle, one hole state, and then you de-excite it, and then you're back to the ground state. So the operator here, when it acts on the ground state, it can create an intermediate state, which is of a one particle, one hole nature. And then after some time, if you think of this time as if this is an initial time T0, and this could be a final time TF, at a final time TF, you de-excite and you're back to where you started. So you see that these diagrams, they can be given this kind of physical interpretation, but you shouldn't really take it too literally. So this is just a way to illustrate algebraic expressions you have in many-body perturbation theory or Green's function theory or any of these many-body methods. And the reason for that is that in principle, what happens in real life is that you have an infinity of interactions in the system. So this means that you should actually have such terms to infinite order. So you can think of this within Heisenberg's uncertainty relation. The system interacts an infinite number of times. Any questions? So the diagrammatic way is a way to, help us in building up a kind of intuition. And you can also see from the diagrammatic approach, as we discussed earlier, if you have a one-body operator acting on the vacuum state, you can at most produce a one particle, one hole excitation. And then, One
question about the ordering of the diagram.
Yeah.
How do you know that you keep order? What's the...
So the way you're set, we are coming back to that when you come to time-dependent perturbation theory. Then it's easier to see it. So now I'm just thinking of these vertices being fixed in a specific hierarchy. Yeah. So the way you can think of it, yeah. If you look at the second order term, the delta E to second order, this is given by you taking an expectation value. It's a vacuum to vacuum expectation value, but where you now have this Hamiltonian, and then you have an intermediate state here. So in principle, there's no time here. So time is just something I have introduced as a way to develop a physical understanding. So you would have phi 0 here, and then you have the denominator, W0 minus Wm. This is Rayleigh-Schrödinger perturbation theory. So you could think of now a kind of interpretation where the system is in a vacuum state, there is an interaction, then the system stays in an intermediate state, and then after some time, the system interacts, there's an interaction again, and then it brings you back to the vacuum state.
This is the ordering of keeping the diagram.
Yes, so when you do time-dependent perturbation theory, then this kind of ordering pops up naturally. And we will see that tomorrow when we discuss time-dependent formalism, because that's the kind of basis when we do Green's function theories. As of now, there is no time here. So you could just think of this as just algebraic equations, which come from you setting up a Taylor expansion in terms of these energies.
The ordering comes start from the bottom.
Yeah. So you can think of, if you go back here, you can think of you being here, then something happens, you have some perturbations, and just like you going for a ride, I mean, your pulse was 50 before you started the ride, then it goes up to 100, and then after some time, you're back to 50. Yeah. So you can think of it in a similar way. And there is a basic assumption, which we will also discuss tomorrow, which is called the adiabatic hypothesis. And that means that these interactions take place in very tiny fractions of time. So the formalism as we have developed it is essentially a Taylor expansion. And in principle, there is no time. So everything we're doing here is just a way to add a physical interpretation to the theory. And it's a handy way. It's a useful way. of expressing contributions, because you can just look at the term and say, okay, this is a two-particle, two-hole excitation. Whereas if you look at the expression we started from, this is where we started, then you would have to look at the different Slater determinants you can make. So one of the Slater determinants here could be a one-particle, one-hole. If this contains a one-body piece, if you have a two-body operator, it can also produce a two-particle, two-hole excitation. And then these are just ways. So this is the one-particle, one-hole. And this is your two-particle, two-hole intermediate state. So it's just a way of, in a compact manner, to just write down a specific contribution. This is the way I like diagrams, and also people have used diagrams to generate the terms in perturbation theory, because you can set up with these rules, you can actually generate higher order terms. So you can generate contributions in third order, fourth order by using the rules for constructing the diagrams. And that gives a very powerful recipe. However, when you go on to fourth order perturbation theory, depending on whether you have systems where you go from the vacuum to the vacuum state, or if you have open systems, then you can get thousands of diagrams to fourth order. Just ask me, because I did that for my PhD. And I don't recommend doing it. Okay. It was a fun exercise. But yeah, if I ask you guys to do a thesis where you write down all diagrams to fourth order, you should protest. You can actually automatize many of these terms. But you see, it's a handy tool. Unfortunately, in some field like particle physics, this has almost been extended to the fact that you view this as the physical process taking place. But in principle, you have to go to infinite order for many theories, unless things have a seeming convergence, or the terms become smaller and smaller as you go order by order. That's the hope normally. And you will see that in an example which we are going to look at after the break. But let's look at the more rules here. So what we're going to do now is actually to look at an explicit evaluation of diagrams. So you can look at a diagram, and from that, you can immediately say whether this diagram should be zero. And this applies to the second midterm, because you can actually look at the contributions in a diagrammatic way. And based on your Hamiltonian, you can say that there is no need to calculate that one, because that has to be zero. And I will give you an example. Or just to give you an example, if you look at this diagram which you have here, and you think in terms of a Hartree-Fock basis, this term here could be zero if you have a Hartree-Fock calculation. And you remember that when we used the Hartree-Fock basis, the one particle, one hole excitation, because then this was the same when we calculated that matrix element, that was the same as I times this operator, this overlap here between a whole state and a particle state. So if we have a Hartree-Fock basis, this is actually equal to zero. So if you run a Hartree-Fock calculation, you could immediately put this contribution to zero. So based on the type of calculation you've done, the basis you're using, you can actually get rid of some of them. The case you're going to look at in the midterm is a case where we are only going to look at the system where the Hamiltonian conserves the number of pairs. So you cannot break a pair. So meaning that you cannot break a pair would also mean that this diagram here would have to be zero, because you cannot break a pair. But one which would not be zero would be this one, because then you could have your initial state here, this one, which can be paired. So that means that they are just in the same single particle state, but with opposite spins. That's the basis for the pairing Hamiltonian. and this was what was used to explain superconductivity. Then you promote then and you construct a pair of two particles above the Fermi level. So with that Hamiltonian, what you will see is that automatically this term can be non-zero, whereas this term here has to be zero, due to the symmetries you want to keep. So having this kind of diagrammatical approach, where you express all terms to a given order in perturbation theory, allows you to say, okay, with my Hamiltonian and with my basis, there are specific terms which have to be zero. And then I can just focus on few terms, because in principle, if you look at this sum here, that sums over all possibilities. And you have an infinity of such possibilities. But then with a diagrammatic approach, this kind of more visual way of recognizing physical processes, then, or physical process in a quotation mark, then you can easily say that this term is maybe non-zero, and this has to be zero. So let's look at the explicit evaluation of each diagram here. And it seems that we are a little bit over time here, so let's just take a small break before we... So what we're going to do now is just to perform an explicit evaluation of each diagram. So let's look at the kind of rules which we need to set up then. So the explicit evaluation, we have specific rules for fermions which need to be respected. So for each topologically distinct diagram, what we would do then would be one, we would typically open up or pull open the diagram by stretching these dotted vertices. And if you are now dealing with Hugenholz diagrams, this is normally what people assume as a common starting point. So if you go back to what we had here, we would simply pull up these dots and rewrite them in the way as you see here or here. And then you would assume that like this one would be a topological equivalent diagram of that one. And you would just only draw one of them. So that means that the first thing you would do then is actually to take, if we have this example, so I'm just going to use a diagram as an example here. So if we have this one, you would then pull open. So this should be a whole line. Sorry for that. This should be a whole line. So we would pull open by stretching these vertices, depending on whether this is a one body or two body. So you would pull open, and then you would often draw it like this. And this would be a diagram which has three other ones, as we discussed before the break, which are topological equivalent. Now, I'm just a plain laziness. I'm now not putting labels on the particle and whole lines. Then when you do this, the next point is that each vertex, two-body vertex, each vertex has a contribution which looks like either like this, or if we have a one-body term, which looks like this. So this depends on the type of vertex which we have. So then we need just to pull that off. And these expressions have specific terms, which we then have to plug in when we set up the final expression. Now, there is a new point here, C, and there is a factor, and we discussed that, and this just follows from the contractions which we are doing. So there is a factor which we have to plug in, which is given by -1 to the power of number of whole lines. And that follows from the contractions which we do with whole states. So that each such contraction gives actually a factor of -1. So there is a factor like that. And then there is a factor which has to do with the way when we close the diagrams, which is given by 1 or the number of loops. And NH is the number of holes or whole lines. And NL is the number of closed loops. And we saw examples of these last week. And that means that if we look at that example, which we put up here, this one. So we have A and B, we're putting labels on them, I and J. Then this would now have 2 hole lines. And then we think of this particle-hole interaction, which starts at the same vertex, ends, and ends at the same. This defines a loop. And we can see that when we do the contraction, that gives rise to a factor of -1. And then if we have 2 such loops, then we have a factor of 2. So that gives us a positive factor. Then there is also an energy denominator, as we have seen. So for each interval between the vertices, interval between 2 vertices, what we have then, with the minimum 1 single particle state, that is passive, which means a state above the Fermi level, with at least one state, 1 single particle. So when I say state now, it's a 1 single particle state above the Fermi level. So F for Fermi level. Then there is a sum over, there's a factor. There is a factor which is given by 1 divided by the sum over I less than F. And then we have the whole energies, which we have, minus, so we can have many. I don't specify where this sum ends. And then I have a sum over A larger than F and epsilon of A here. So if we now look at the diagram which we had, this example here. So we have a whole line and a particle line, A and B, the particle lines, and I and J, the whole lines. So if we draw a line between the 2 vertices, so let's mark that in red, then we see that we have, as whole states, we have epsilon I plus epsilon J. These are the whole states. So the sum which we had is I less than F. That brings in these 2 states. And then the particle states, they go over to epsilon A plus epsilon B. So that means in this explicit case, we have a sum over epsilon I plus epsilon J minus epsilon A minus epsilon B. And this is nothing but what we wrote as omega 0 minus this omega m. And if this m was a 2 particle, 2 hole state, so remember now if phi of m is given by a 2 particle, 2 hole state, A, B, AJ, AI, acting on phi 0. That means that this energy, Wm, is then given by epsilon A plus epsilon B minus epsilon I minus epsilon J plus W0. Because we took out the whole states I and the whole states J and replaced them with 2 particles in the states A and B. So that means that this unperturbed energy has to be the new single particle states, the energies of those. And then I have to subtract the energies of the particles which I took out, or the states which I took out, which are I and J. Because here, with this state here, I take away a particle in the state below the Fermi level with index I, and similarly one with J. So that means that these energies should not be included here. And then you see now that when you look at this expression, which we had originally from the perturbation theory expansion, you see now you have omega 0 minus omega 0, that disappears. And then I have minus epsilon I minus epsilon J. that means that this becomes whole lines, whole energies minus particle energies. And then you would simply count the states which you have. So this is a very compact way of extracting the energy denominator by just looking at the diagram. So if you go back to a new example, which we also had before the break, if we now look at this example here, so in this case, the whole line here, I, that starts and ends at the same vertex. So that is not participating in this excitation process. So a K, and we have a J and an A. So now we are looking at the whole lines and particle lines between the two vertices. So that gives us a denominator which has to be epsilon J minus epsilon A, which we saw before as well. So this is the way we would extract the energy denominator. So let's look at another example. It's always useful to look at examples. So let's now look at a diagram like this. And then we have a state here, and then we have an A and B, and then we have an I and J, and this will be a C, and this is a K. So if I look at the denominators here, I would now have, this is a term to third order perturbation theory. And this is a state where we first create a two-particle, two-hole excitation. So we have that here. But then one of the one-particle, one-hole pairs gets de-excited. And then we create a new one-particle, one-hole state. But we still have an intermediate state here, which is a two-particle, two-hole state. That's the intermediate state. But they change two of the one-particle, one-hole guys. Now, the energy denominator here, if I use the same rule, so this one would give me epsilon K plus epsilon I minus epsilon A minus epsilon C. And then I have the next denominator, which then would simply now give me epsilon I plus epsilon J minus epsilon A minus epsilon B. So if I were now to calculate the unperturbed energies for these intermediate states, as we did here, so this one, I would get exactly the same kind of contributions, which I can just read off from the diagram. So there is an energy denominator for every interval between two interactions, which now can be written out in terms of the sum of single particle whole states which participate, and minus the single particle states above the Fermi levels which participate. So you can just look at the diagram and extract the contribution to the analytical expression. Then, so this was point D. There is a point E here, which is also very important. So point E, and we demonstrated parts of it. And there is a factor. There is a factor which is 1/2 to the power of number of equivalent pairs. So this NEP is the number of equivalent pairs. And I'm going to define what we mean by that. So an equivalent pair, that's pairs of lines which begin at the same vertex or same interaction and end at the same interaction. So this can be the same interaction, or it can be a different interaction. So the number of equivalent pairs, if you now look at this example, which we've been having in here. So we have an I and J, and A and B. So we would have A and B would be an equivalent pair of fermions. So they start at this interaction vertex here, and they end at the same interaction vertex. So this rule is actually easy to prove because it follows from the symmetries of the Hamiltonian. So we did show some examples last week, but we didn't generalize it. But actually the rule is pretty simple to show. And then we have with I and J here, if we look at that one, we have two whole states which begin at the same interaction and end at the same interaction. So for this specific diagram, we would have n equivalent pairs to be equal to 2. So we would get a factor of 1 divided by 4. And then the final one is that we would sum freely over all the intermediate states. Over all intermediate states. Now, this has an unfortunate thing. So I'm just stating this in connection with the linked diagram theorem, which we haven't discussed thoroughly at all. So because I can now have states when I sum freely where I violate the Pauli principle, when I look at diagrams. And the thing is that the way we set up many-body perturbation theory here, by summing freely means that when you do it computationally, you won't have an if test. So this sounds like a kind of strange thing to say, because when you're writing a program for calculating these diagrams, you can do that in different ways. One, you can bake in all the physics you know about and put in many if tests in your program. That if they're equal, skip it, and so on and so on. That slows down performance. So you would think that you being brave and baking in all the physics would give you a code which is more efficient, but it's often not the case. So by summing freely, you avoid all the tests. And these are cases which are easier to parallelize, because if you have if test, you lose vectorization and parallelization in setting up the code. So then by summing freely, you can then just let the calculation of these diagrams, as we discussed the week before last week, we could actually rewrite this diagram you see here, or this contribution, in terms of matrix-matrix multiplications. And you would have matrix elements which are possibly 0, but that is actually more efficient than actually baking in all the physics tests. It sounds strange. I've been testing this with, when you have many single particle states. When you have few, then it doesn't matter. So summing freely has a consequence, which is a little bit deeper also than just these simple computational issues. Because summing freely can lead to Pauli violating diagrams, as we will see. But these diagrams are needed in order to cancel what's called unlinked diagrams, which are unphysical. And the unlinked one comes when you do many-body perturbation theory with Rayleigh-Schrödinger perturbation theory. And I will show you in a simple example how these type of diagrams appear. So there are some subtle arguments here, which you will see discussed in the literature as Pauli violating diagrams and unlinked diagrams. Yeah?
When you're stating some freely, this means sum over all.
Without constraints.
Yeah.
So I don't use any symmetries which would come from the interaction. So I don't use the fact that you would tabulate your interaction matrix elements in a specific way to save space. I just set up freely all single particle states. And we will see examples of that. So this statement sounds innocuous. And the way we actually set it up was like that. So if we look at this diagram, which we have this term here, we have now 1 divided by 2 to the power of number of equivalent pairs. We have 2 whole lines. We have 2 closed loops. And then we are summing freely. And this is actually what you see here is the contribution which we got by simply calculating the different matrix elements. And then we are setting up the matrix elements, ij. So now we are using the rules for that diagram. And then we have an AB, V of ij. And now I'm skipping that the matrix elements are anti-symmetrized. So I'm just assuming that they are anti-symmetrized. And then we have an epsilon I plus an epsilon j minus epsilon a minus epsilon b. And this becomes simply equal to 1 divided by 4. And then we have this a, b, I, j. and with the matrix elements ij, v, a, b. And then I just write this squared. And then I have epsilon I plus epsilon j minus epsilon a minus epsilon b. So this is an example of how we can use diagram rules to calculate what we calculated before. So just some time ago, we calculated this contribution and found exactly the same expression. So let's look at some other examples here, just to gain some kind of practicing. If we look at the next example, we could take this diagram here. So we put labels on them. And we assume that we started with a Hugenholz diagram. So we are going to use anti-symmetrized matrix elements. So I have an A and B, I and J, C and K. So where we started was with something like this. So we have these two guys here and these two guys here. So we have C, K, and we have B and J. And then we have the line here, which is A, and then we have this one, which is J. No, sorry, I. So this is the way you would write it in a compact notation using the Hugenholz diagrams. And then you would open it up like this because it's easier to see the expressions you need to set up when you have this. Now, in this particular case, the number of equivalent pairs is equal to 0. So we don't have two fermion lines which begin at the same vertex and end at the same vertex. So there are no cases like that here. But then we have the number of whole lines, which is equal to 3. And then we have the number of loops. So we have one closed loop here, one closed loop here, and one here. So we get a number of loops equal to 3 here. And then we can plug in the matrix element. So we have a plus. We don't have a factor of 1/2 because we have no equivalent pairs. So we would sum over A, B, C, and then I, J, K, like that. And then we have the matrix elements. So we start typically at the top. So we have I and J. So we have I, J. And now I'm skipping anti-symmetrized matrix elements. So I have A and B. And then I have the next one, which is B and K. So this is a particle, one hole excitation. And then I have my J, the whole state. And then I have C. And then finally, I have the last element, which is A of C, of V, and then I have I and K. And then I have the denominator. So the upper denominator, which would be this one I get from here, that gives me an epsilon I plus an epsilon J minus an epsilon A minus an epsilon B. And then I have the next one, which comes from this one. And that gives me an epsilon I plus an epsilon K minus an epsilon A minus an epsilon C here. And then I can continue. So sometimes people would like to keep only specific terms. Some of these terms can be summed to infinite order, like this one particle, one hole diagrams. And that leads to what is called random phase approximation in physics. Some of you may have heard of that. That's a very popular approximation in mean field theories, where you can sum one particle, one hole excitations to infinite order. And these are important to resum to infinite order because it gives you a finite contribution. Actually, if I take this contribution here and look at the electron gas, I will actually get that divergence. So order by order, the electron gas would give me divergent contributions. But I can remedy that by summing these type of diagrams here to infinite order. And that can give me a renormalized interaction, which I then can use in other contributions. That's a strategy which is often used you can sum some contributions which deal with the long range part of the Coulomb interaction. And then you will go back to those which were not included and calculate these order by order, hoping that they are small and that you can truncate the rest of your perturbation expansion at a given order. So this is often what you would do in physics when you have a specific interaction like the Coulomb interaction. If you have an interaction which is repulsive at short distances, you would sum two particle excitations to infinite order and then reuse that in a calculation of diagrams like this. And then again, hope that these terms become smaller and smaller as you go in higher and higher orders. So keep in mind, there is no guarantee that perturbation theory converges. So a priori, you don't know if it converges, unfortunately. But it is a useful recipe to get some kind of feeling of what the different contributions can be. Now, the thing which I wanted to say a little bit about now is an example where we can illustrate some of these things and rewrite the contributions, the algebraic contributions in terms of diagrams. So let's try to mix both the algebraic approach and the diagrammatic approach. And then this is going to point to some consequences for link diagrams and these Pauli violating diagrams. So let's take a look at a simple example. So we are going to set up a Hamiltonian here, which is a system you can think of as a one particle system or just as a simple two-level system. And we have a simple Hamiltonian. So let's assume that it's a one particle case. And we have two states. So this is an unperturbed state epsilon 1 and an unperturbed state epsilon 2. So there are only two single particle states in the system. So this is a simple world, which I like. And we have a Hamiltonian now, which is simply a sum over I equals 1 up to 2. There is a one body part times epsilon I. And these states which we have here, which I'm going to call phi 1 and phi 2, these are eigenstates of this piece, which is our useful H0. Okay? So we are just going to make a perturbative expansion around epsilon 1 and epsilon 2. And then I have a Hamiltonian here, an interaction piece, which I have defined so that I is different from J. And this is going to lead to some simplifications for us. So I have an AI and then an AJ. So it's a simple Hamiltonian, which we can solve analytically. And then we can do many-body perturbation theory. Either we do Bruyère-Wigner or Rayleigh-Schrödinger. And then we can look at which diagrams pop up in these different contributions. So just to anticipate, what we can do here is to diagonalize the Hamiltonian, which we have here, and Taylor expand the energies around the lowest one, and that will give us Bruyère-Wigner perturbation theory. But when we Taylor expand it, when we solve the exact one, that's going to be the same as Bruyère-Wigner. But when we Taylor expand the lowest energy, we will get something which will be comparable to Rayleigh-Schrödinger perturbation theory, order by order. But let's look at these different matrix elements which we have here, because there are some basic things. I'm going to use this to repeat a little bit about many-body perturbation theory as well. So let's just take a closer look at this specific Hamiltonian. So what we have now is that this H0 acting on one of these states is going to be given by either epsilon 1 or epsilon 2. Sorry, epsilon phi of I. So this is the basic assumption we made. That's the basis we're going to use. And if I look at this HI here, when I write it out, this is going to be given by a lambda times A1 and A2 plus A2 dagger A1. So that's a simple Hamiltonian which I'm setting up for the interaction piece. So what you see here is the following. If I use this one and I calculate the matrix elements of the same state, this interaction piece, you see that that is equal to 0. Let me just try to convince you that that is the case. So that is the case if you now just take any of these states. So let's suppose you take 1, then you would have a lambda here, and then I have A1 dagger, A2, plus an A2 dagger, A1. And this is acting on phi 1. And phi 1, in this case here, is just an A1 dagger acting on a true vacuum. And phi 2 is equal to A2 dagger acting on a true vacuum. Okay? And then if we just take any of these terms, it's pretty easy to see that they have to be 0. So when I take the diagonal matrix elements, I mean the expectation value from phi 1 to phi 1, that is going to be 0, and the same with phi 2 to phi 2. So you can see that immediately now, because what I'm going to have is 0, and then I have A1, and then I have a lambda, which I can pull out here, and then I have an A1 dagger, A2, plus A2 dagger, A1, and this is with A1 dagger, and then 0. And what you see now is that the first one, A1, with the A1 here, this one is obviously non-zero. That is just delta 1, 1. But then I have to match A2 with A1, which is 0. And then you see the next one here. If I take A2 with A1, which is the only possibility I have, that is 0 immediately. And the same if you now replace phi 1 with phi 2, you get exactly the same. So that means that when I set up the Hamiltonian matrix, I'm going to get a simpler matrix here. So the Hamiltonian matrix, which we are going to diagonalize. So H is then for these two states. So this is FCI, okay? Just FCI with a 2 by 2 problem. So what I'm going to get then is the following. I have epsilon 1, and then the interaction piece is 0, right? So that's just becoming 0. And then I'm going to have a phi 1 here with HI with phi 2. And then here I'm going to have a phi 2 of HI phi 1. And then I'm going to have epsilon 2 here, because the diagonal term has only the unperturbed energy. And then it's also easy to see that when I take phi 1 of HI with phi 2, this is simply going to be equal to lambda. Okay, this parameter. You can see that immediately. So let me just do that. And if you take, you have 0, and then I have an A1, and then I put lambda outside here. And then we have a A2 dagger, AI, A1, A1 dagger, A2, acting on A2 dagger of 0. And now you see that this one gives me something which is different from 0, but then this matches this one. The second term, however, gives 0. So the one which I mark in red here, that brings A1 to A2, which is 0. So that's 0. And then I have A2 with A1 here, which is also 0. So the only term which survives here is actually this one. And you see now that this is just equal to lambda. And then the determinant which we have to, put to 0, which we want to solve. So what we have then to solve is det of H minus an energy, and we want that to be 0, okay? So the equation we want to solve then is actually this determinant epsilon 1 minus the energy, and then I have lambda, and then lambda here, and then epsilon 1, epsilon 2 minus E. And we want this determinant here to be equal to 0. Okay? And this is something which we know how to solve. So we can then find the energies, and if we do that, what we would find if you look at the lowest energy. So let's look at E1, and we assume that that is larger or smaller than E2. So this is the ground state. It's a low energy because we just get a second order equation to solve. So what we have then, when we plug everything in, so we would get an E1 here, which is now equal to 1/2 when we solve the equation of epsilon1 plus epsilon2, and then I have minus. So I take the lowest one instead of plus. So, you know, this is just a standard second order equation. And I have epsilon1 minus epsilon2 squared plus 4 lambda squared. So that's the energy. And now what I can do is I can Taylor expand this energy if I want to. So let's do that. So what I could do is to rewrite this one in terms of 1/2, and then I have epsilon1 plus epsilon2, and you will see now why I'm going to rewrite it in terms of epsilon2 minus epsilon1, because it's going to cancel a term for me. And then I have this is multiplied with the square root of 1 plus 4 times lambda divided by epsilon2 minus epsilon1, and this is just squared. And then I can Taylor expand around this lambda divided by epsilon2 minus epsilon1. So if we Taylor expand, what we are going to get then is an epsilon1, which is going to be equal to 1/2. And then I have epsilon1 plus epsilon2 plus, no, sorry, minus epsilon2 minus epsilon1. And this is now multiplied with 1 plus, and then I'm getting terms which run like 4 times lambda squared divided by 2. And then I have epsilon2 minus epsilon1 squared. And then I have minus. So I'm just setting in the geometric series here to the power of 4. And then I have epsilon2 minus epsilon1 to the power of 4. And this goes up with many, many more terms to infinite order. And now you see immediately why I wrote it like epsilon2 minus epsilon1, because then when I take the first term, this simplifies simply to epsilon1 minus lambda squared of epsilon2 minus epsilon1 plus, and then I get lambda to the power of 4 of epsilon2 minus epsilon1 to the power of 3. And then this goes minus and plus up to infinite order. So what we are going to show now is the link between many-body perturbation theory approaches like Bruyère-Wigner perturbation theory and Rayleigh-Schrödinger perturbation theory. So we're going to link, so what we did now was simply to Taylor expand. So what we want to do is to link this with Bruyère-Wigner perturbation theory, BW perturb theory, and Rayleigh-Schrödinger perturbation theory. And then we're going to see the differences. So what we're going to see is that Bruyère-Wigner perturbation theory, which depends on the exact energy, is going to give us the exact result. On the other hand, Rayleigh-Schrödinger perturbation theory is going to give us this Taylor expansion. So it's a nice example because we can use this simple case of a 2x2 matrix to link with different perturbative expansions. And that hopefully gives us a little bit more insight about what these expansions are about. So in order to link this, let's now look at the Bruyère-Wigner perturbation theory. This is one of these words which I always struggle with. It's like you have this word susceptibility. I always have to rethink about it. Whereas the way I grew up in Italy and the way you would say it, it just pops out. And it's much more difficult. It's suscettibilità. But when I say it in English, it's so there are some words, I'm just going to say BW, okay? I can't explain it, but it's like that. Okay. So when you look at the Brienne-Wigner perturbation theory, then we would have the so-called correlation energy, which then would have, when we now are looking at the ground state only. So this is in terms of the interaction piece, only that. That's the way we have defined perturbation theory when we set up the correlation energy. And then we have a phi I of hi, and then the intermediate state is phi 2 of phi I. And this is divided by, but now I have the exact energy. I don't have the unperturbed energy, but this is divided by epsilon 1 minus this unperturbed energy. And then I have the term to third order. And this is where we're going to stop today. And I will try to finalize this example tomorrow. And this is divided by epsilon 1 minus epsilon 2 divided by epsilon 1 minus epsilon 2 here. Now, and then we have high order terms, plus plus. But the thing which you see here immediately is that this one is 0. By the way, we have defined the Hamiltonian. And this one is also 0. So all these terms, the higher order terms, are going to be 0 because you will have contributions where you go from the same state to the same state. And by the way we have constructed this Hamiltonian, this is exactly equal to 0. So the reason why I did this kind of Hamiltonian was simply to be able to do that. So that means that delta E here is going to be equal simply to lambda squared of E1 minus epsilon 2. So the total energy then, when I add up, I know that the total energy E1 is epsilon 1 plus delta E. This is the way we have defined this, the unperturbed energy plus the correlation energy. And that is the same as epsilon 1 plus lambda squared of E1 minus epsilon 2. Now I take E1 minus epsilon 1 and I multiply away with E1 minus epsilon 2, and this is equal to lambda squared. And this can be rewritten as E1 minus epsilon 1 or E1 minus epsilon 2 minus lambda squared equals 0, which is the same as the determinant of epsilon 1 minus E1 lambda epsilon 2 minus E1 equal to 0. And this is the exact solution we have. So Brienne-Wigner perturbation theory, with this specific example, stops at second order. And this is the same as the exact solution to the problem. However, we don't know E1. And that's the problem with Brienne-Wigner perturbation theory, that E1 is the quantity we want to find. So Rayleigh-Schrödinger perturbation theory has this advantage that we can calculate order by order, but then we need to include, in this simple example, terms to infinite order. So tomorrow we're going to look at how we can rewrite this in terms of diagrams and what this contribution here actually means in terms of diagrams. And then we are going to go back to slides and we will remind ourselves about these pictures. And we are going to look at time-dependent perturbation theory, the adiabatic hypothesis, and then try to link this with Green's functions. And that will be the last topic we deal with.